Welcome to TechDaily.ai. I'm David, and I'm joined today by Sophia.
Great to be here.
Our mission for this deep dive is to shortcut you straight to the cutting edge of AI infrastructure. We're taking a deep look at the massive technological shift required to scale AI.
Yeah, we're talking about why current data center architecture is hitting a physical, a thermal, and an electrical wall.
And how some pretty exotic materials are suddenly creating the blueprint for, well, the next 2 decades of computing. This isn't just an upgrade, it feels like a total reinvention.
It really is.
But before we jump in, a quick word from our sponsor. This deep dive is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup disaster recovery, hyper-converged solutions for VMware, Hyper-V, and Proxmox clusters, AI servers, and SA365, a turnkey security appliance designed to protect your hybrid environment, as well as comprehensive public and private cloud services. Check out stonefly.com for more info. Okay, so let's unpack this. We have to start with the sheer scale of the crisis we're facing. I mean, the growth in AI infrastructure is so staggering that we are literally reshaping landscapes.
That scale is the fundamental problem. You look at the energy draw. A single next-generation AI campus built for foundational model training now pulls 1 to 2 gigawatts of power.
1 to 2 gigawatts. For our listeners, can you put that in perspective?
That's the power load comparable to an entire major metropolitan area, just for one computer campus.
And you can already see the strain, right? In places like Northern Virginia, which is a huge hub, data centers are already consuming a quarter of the entire electrical grid.
And that demand is just accelerating. But what's really fascinating here is that the real bottleneck isn't even the raw compute power itself.
You mean the energy for the chips actually doing the work?
Exactly. The problem, the real choke point, is the sheer volume of data being moved between those chips.
That's a crucial distinction. We're not running out of transistor power. We're running out of ways to connect them fast enough.
Precisely. I mean, you look at a project like Meta's Hyperion facility, it's designed to scale up to 5 gigawatts. It's a computer the size of Manhattan with over 1 million GPUs.
So it's not a collection of servers anymore.
No, it's one single massive AI supercomputer. And when your workload spans that entire facility, every tiny micro delay between the chips becomes a critical failure point. The network stops being a connection and it becomes the computation itself. The bottleneck is right there between the chips.
And that bottleneck for decades now has been copper. I mean, copper carried the entire digital revolution. A single hyperscale site can use 50,000 tons of it.
It was the backbone. But now it's holding us back. It's the Achilles heel of high-speed AI.
Why, though? It works fine for so many things.
Well, it does at slower speeds.
Yeah.
But the moment you start pushing tens of gigabits per second, which is the minimum for AI, that signal range just shrinks. It goes from hundreds of meters to a few meters.
Or even inches if you push it faster.
Or even inches, yeah. It just collapses.
So why does speed kill copper? What's the physics behind that?
It comes down to resistance and something called attenuation. The faster you push an electrical signal through copper, the more energy the wire itself just absorbs. The signal gets weaker and weaker until it's just noise.
So to keep it alive, you have to boost it.
You have to stack up equalizers, amplifiers, retimers, all these little components along the way.
And every single one of those burns power and generates heat.
Precisely. And that heat is the great silent killer here. We found that almost 40% of the total power in a modern data center doesn't go to the AI chips. It goes straight into fighting the heat generated by the network.
40%. Just for cooling and boosting the signal.
Yeah, it's a point of diminishing returns. You can literally double your processors and get almost no speed up because the copper network is just suffocating the data flow.
This copper is maxed out. It's done.
It is. If the electrical signal is failing, the only viable medium left with enough runway for the next decade is light.
Photons.
Photons. Once your information is writing on photons, all those painful electrical constraints they fall away. They don't grind through resistance. They don't spill energy as waste heat when you push them faster or further.
And that's where it gets really interesting. It's like switching from, city traffic to a dedicated, frictionless train on its own rails.
That's a great analogy. And optics is already the backbone of the internet. It's used for rack-to-rack links. It's everywhere.
Everywhere except the one place you need it most.
Exactly. Right next to the compute. There's still this mandatory electrical path, a short copper hop between the chip die and the optical switches outside.
The last 2 centimeters.
That's what they call it. And that's where all the power, latency, and heat spikes are concentrated. The industry has been stuck on that last little hop for over a decade.
So bringing optics onto the chip itself seemed like the obvious next step, but it turned into, what, a massive physics nightmare?
A total nightmare. The problem was never the glass fiber. It was the tiny devices that translate electrical data into light pulses, the modulators.
And what was the trade-off there?
Well, you had a painful choice. You could use traditional modulators like the Mach-Zehnder interferometer, which are great, but they're enormous by microchip standards, just too big to fit next to tiny transistors.
Okay, so the big ones don't fit. What about the small ones?
The small ones, like microring modulators, are incredibly fragile. A temperature shift of just 2 degrees Celsius knocks them completely out of tune.
2 degrees. A GPU can jump from 30 to 90 degrees Celsius in seconds under load?
Right, so you can see the problem. How can you put this incredibly sensitive optical tuner right next to a chip that behaves like a rapidly heating oven? Thermal stability was the hill where all these optical ideas just died.
But something changed. And it didn't come from one of the huge corporations. It came from a research hub in Belgium, IMEC.
That's right. Their expertise is in material science, which is exactly what was needed. They realized they needed a materials-based solution for two things: a stable light source and a data encoder, the modulator, that could survive that thermal chaos.
Okay, so let's start with the light source. Silicon is great for transistors, but we know it hates emitting light. Why is that?
It's what's called an indirect band gap semiconductor. Basically, when electrons lose energy inside silicon, it comes out mostly as heat, not as a clean photon of light.
So you need a material that loves producing photons.
And they settled on gallium arsenide. It's incredibly efficient at generating light.
But wait, gallium arsenide is famously expensive and hard to manufacture? Silicon wafers are huge and cheap. How do they solve that? Because manufacturing is everything.
That was the core innovation. It was a tiny geometrical trick. They carved microscopic V-shaped trenches into the silicon wafer.
Into the silicon itself.
Yes. And when they grew the gallium arsenide inside those tiny trenches, the walls trapped all the crystalline defects. This let the gallium arsenide crystal align perfectly on top of the cheap, massive silicon wafer.
That's fascinating. So it's a structural fix to combine two totally different materials at scale. So you have the light. Now you need to encode data onto it with the modulator.
And again, silicon's too slow for that. So the trail led to silicon-germanium, SIG.
It's right below silicon on the periodic table, right?
Exactly. It's similar enough to integrate, but it reacts fast to electric fields, and chronically, it's thermally stable. It doesn't suffer that same drift as the old ring modulators.
But I've heard there's a problem there too, something called lattice mismatch. Can you explain that?
Sure. Imagine trying to stack two different sized Lego blocks. The internal crystal structure of silicon-germanium is slightly different from silicon. If you just stack them, they create stress and defects.
So how do they fix it?
They had to optimize the growth layer by layer, almost like creating a buffer to mitigate that stress. And they had to tune it very carefully to keep something called dark current low.
And what is dark current for those of us not in a physics lab?
It's basically electrical leakage. It's current that flows even when no light is being modulated. If that gets too high, the device burns too much power and generates heat, which defeats the whole purpose of switching from copper.
So the result of solving both the light source and the stable modulator
Snapped everything into place. IMEC built a microscopic modulator that can push 440 gigabits per second per lane. That's more than double the industry standard,
500 billion pulses every second.
with a fraction of the power of copper. And this combination, the gallium arsenide laser plus the silicon-germanium modulator, that's what finally crosses the last 2 centimeters.
And the commercial proof came pretty fast. I mean, Marvell just acquired Celestial AI for over $3 billion, right? That's a huge bet on germanium.
A massive bet. It proved the fundamental physics could scale. So now the industry is in a gold rush, betting on 2 major commercial paths.
Okay, let's talk about Path A. This is coming from the biggest player, TSMC. They're developing something called CUPE.
CUPE stands for Compact Universal Photonic Engine. It's co-packaged. It takes a high-speed electronic chip and bonds a new photonic chip right next to it, micrometers apart, all inside one package.
So the handoff from electron to photon is almost instant.
Instantaneous. It unlocks terabit speeds, it slashes power by at least 3 times, and it gives a clean, scalable path to building those million GPU AI factories. IR Labs just unveiled the first chip using this CUPE tech, so this is happening now.
Okay, so QPE is the, let's say, the conservative high-volume path.
Yeah.
What's the moonshot? That brings us to path B.
The optical interposer. This is a much bolder approach from teams like Lightmatter.
And their tech is called passage. So instead of side-by-side, they put an optical layer under the processor.
Yes, it's an elegant solution. It allows the thousands of tiny chiplets inside one giant package to talk directly to the outside world using light. Data flows vertically, straight down from the chiplet into the photonic layer.
So every piece of the chip gets its own personal light-speed exit lane. No more crawling across the chip to get out.
Exactly. And that's why they're claiming speeds up to 64 terabits per second compared to the 6 to 8 terabits for early CU. Data is never waiting in line.
And the cost implication here is huge. Today's pluggable optics cost, what, 70 cents per gigabit?
Roughly. But integrated optics, whether it's CUPE or the interposer, costs significantly less per gigabit. You get a massive performance boost for a radically lower cost. It's an economic necessity at this point.
So what does this all mean for the bigger picture? Every major leap in human capability came from better ways to compute and move information. Copper got us to early AI.
And light is what will push us to the next milestone. I mean, this is the clear continuation of Moore's law. The speed of AI isn't about one chip anymore.
It's about how fast hundreds of thousands of chips can act as one unified computer.
Exactly. And if we bring this back to the core science, the big question now is reliability. TSMC is scaling COPE now, that's the safe bet. But the ultimate success of silicon-germanium, can it survive years of stress and keep that dark current low?
It's an all-or-nothing bet.
It's an all-or-nothing bet that determines who controls the gateway to 200 terabits per second per rec and who basically controls the architecture of future AI.
A fascinating future. And before we wrap up, a final word from our sponsor, Stonefly. As we've discussed, these massive data sets require unprecedented storage and security. Be sure to check out the 100 TB immutable and air-gapped SSO NAS starting at just $8,995. It's a powerful solution designed to give you the enterprise-level storage and security you need to handle the mission-critical data we talked about today.